The second unit we're going to be doing is called roots and powers. So in this unit, we're going to be taking the square roots, third roots of numbers, as well as applying our exponent rules that we learned back in grade 9. We're also going to be adding a couple more exponent rules. But to start off, let's just look at our introduction to roots and powers. So firstly, we need to know the different parts of a radical. So let's go over them here. So to start off, we have the radicand. So that is the big number on the inside of a radical symbol. So a radical symbol is that check marky looking thing. Then we have the index. The index is the small number. That tells us what root we are taking. So if we're taking the square root, if we're taking the third root, and so on. And then finally, whenever we have a number out front of something, we call it the coefficient. If it's out front and it's multiplying it, we call it the coefficient. So in this case, the 5 here is multiplying this entire radical. So it is the coefficient of the radical. Now, this is important down here. It says, if the index is not shown, it is implied to be 2. So up until this point, you've probably mostly just seen the square root of 16 is equal to 4. Now, in this case, there is nothing in this index spot right here, but there's actually an invisible 2 because we're taking the square root of the 16. So every time we have a radical sign, if they don't put a number where the index is supposed to be, there's actually an invisible 2 there. So let's look at example 1. It says evaluate the following radicals and identify the radicand and the index. So if we were to evaluate them, evaluate in math always means to solve. So the square root of 16, oh, we just did that up there. That's 4. And the radicand in this case, radicand is the big number underneath the symbol, so it is 16. And the index, that's the smaller number, that is a invisible 2. So remember, if there's no index given to you, there's technically an invisible 2 there. On the next question, B, we have the third root of 64. So we need to think what number times itself 3 times is equal to 64. In this case, it would be 4, once again, because 4 times 4 times 4 is equal to 64. Therefore, 4 is the third root of 64. So then we have the radicand here. That's the bigger number. That is 64. And the index is 3 this time. So over here we have a list of perfect squares and perfect cubes, as well as a visual representation of perfect squares and perfect cubes. Now what these visuals are telling us is that this one here, we have 9 square units. Well, it's actually telling us that the square root of 9, because we're dealing with a square shape here, so the square root of 9, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9 little boxes in there, the square root of 9 is equal to 3, which is the side length of the square. We can think the same thing with this cube here, but this time we would take the cube root of this number here. So we are looking at the cube root of 27, and we're saying cube because this shape here is a cube, and it is equal to the side length, which is 3, once again. And that's because 3 times 3 times 3 is equal to 27. So now let's look at estimating square roots and cube roots. Now this is something you did in grade 9. I'm not sure if you estimated cube roots in grade 9, but it's the same thing except with perfect cubes as opposed to perfect squares. So this is how I teach estimating square roots in grade 9. Because remember, we're not allowed a calculator in this unit, so we need to be able to estimate some of these numbers. So let's look at the square root of 20. So what I would do is I would make a little timeline here, a little number line, sorry, and I would put the perfect square just below 20. So in this case, it's 16. And then I would put the one just above 20, which is 25. Now I know the square root of 16 is 4, and the square root of 25 is 5. So I know that the square root of 20 lies somewhere in between 16 and 25. Well, 20 is slightly closer to 16 than it is to 25, right? It's only 4 away from 16 and 5 away from 25. So I would place it somewhere here on our number line, square root of 20. So then if we were to estimate a number that would lie down here, which number would be in between 4 and 5 that would lie just about here? I would say about 4.4. So I'm going to say that square root of 20 is approximately equal to, and those two squiggly lines mean approximately equal to 4.4, because remember, this is just an estimate. So let's do the same thing, except this time with a cube root. So I'm going to make my little number line again, and we need to think of the perfect cube just below 82. So that would be the cube root of 64, and then the one just above 82 would be the cube root of 125. So if we took the cube root of 64, we'd get 4. And if we took the cube root of 125, we would get 5. So we know the cube root of 82 is somewhere in between 4 and 5. Now, I would say 82 is definitely closer to 64, so I'd place it somewhere about here on our number line. So a good guess for this one would be 4.2 approximately. So the cube root of 82 is approximately equal to 4.2. So in example 3, we want to order these numbers from least to greatest. Now remember, in this unit, we're not allowed a calculator, so we need to get good at estimating these things. So we would make a little number line for each of them and give a good estimate. So if I'm thinking of let's start with the cube root of 13. And I guess I didn't leave that much space here, I apologize. So we'll have cube root of 13. So we need the cube root just below 13. So that would be 8, the cube root of 8, which is 2, and then the one just above 13 would be 27, which would be 3. So we know the cube root of 13 lies somewhere in between 2 and 3. It's going to be on the number line here closer to 8 than it is to 27. So I'd place it somewhere here. So I'd say it's approximately 2.2. So looking at the next one, the square root of 18. The square root of 18, the square root just below 18 would be the square root of 16, which is 4, and the one just above 18 is 25. So then here, 18 is definitely closer to 16 than 25, so I would say it lands over here, so I would say 4.2 in this case. For the next one, we have the square root of 9. Oh, well, that's easy. We don't even have to estimate that one. We know the square root of 9 is 3, so we're good there. Let's go on to the fourth root of 27. We don't really think about fourth roots very much. So the fourth root of 27. So let's think of some fourth roots here. Let's try, and this is just rough notes down here, 2 to the power of 4. What does that give us? Well, it's 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the power of 4 is 16. So I'm guessing that's going to be the one right below 27. So the fourth root of 16, which is 2, meaning we need to do 3 to the power of 4 to get the one just above it. So that's 3 times 3, which is 9, times another 3 is 27, times another 3 is 81. So the fourth root of 81 is 3. So if we're looking at where 27 falls on this number line, it's definitely close to 16 than it is to 81. So again, I would place it probably over here, 2.1, something like that. And finally, we have a third root of -5. So if the index is an odd number, we can actually take the root of a negative number. It's a little rule in math, but let's see why. For example, if we had -2 times -2 times -2, that would equal -8. Therefore, the third root of -8 is equal to -2. So we can take the third root of a negative number. We could also take the fifth root. So as long as the index, meaning this small number here, is an odd number, we can take the root of a negative number. So if we're doing our little number line here, now we're moving in the negative direction. So I actually gave us one of the answers here. Let's put the third root of -8 here, which is -2. So we know over here we're going to have the next number, which is -1. Because remember, if we're imagining this as a number line, this would continue to 0 and 1, 2, and so on. So The cube root of what gives us -1? Well, that would just be the cube root of -1. So if we're placing -5 on here, that's slightly closer to -8 than it is to -1. So I'd place it somewhere over here. So this would be like -1.7, let's put. So now in part B, and let me just erase all this here, we're going to use our calculator to check our estimates. Let's see how close we were. So I'm going to plug all of these numbers here into my calculator and see what I get. Now, on your calculator, you're looking for a button that looks something like this. It would have a Y here with the root sign and then an X. Now, if you need help plugging these into your calculator, let me know. But that being said, for this unit, we aren't using a calculator for it. For this example, we're just checking our answers. So I just plugged all 5 of these into my calculator, and here are the actual answers that I got. So if we compare these to my estimates here, some of them are spot on, some of them are a little bit off, but you know what? That's why they're considered estimates. They're just close guesses to what the roots are. So now we have to place these roots in order from least to greatest. So let's look here. I'm going to use the ones from the calculator since those are the most accurate, but I could definitely do the same thing from my estimates. So starting off, if we're looking at the smallest one, that would definitely be the -1 there. So -1.7, or in other words, the root of it is 3 root -5. Then we have our next one would be the 2.3, the pink one there. So 2.3 would be next, or the 4th root of 27. Then next we would have the 2.4 that comes right after that. 2.4, or in other words, the 3rd root of 13. Next one would be the square root of 9, which is just 3. So square root of 9. And then finally our red one here, the square root of 18. Whoops, I'm going to put that down here. So we have 4.2, or the square root of 18. So whenever you're putting your final answer for this, make sure you put the roots. Don't put the numbers that we got. I want to see the roots in order from least to greatest. So there we have it. So we're looking at rational numbers. Those are exact numbers. So what I mean by exact numbers are they can be written as a fraction in the form m over n, that just means as a fraction with a number over a number, or they can be written as a decimal that either terminates, meaning the decimal ends, so it doesn't continue off the screen, or the decimal repeats. So in other words, 1.3 repeated, that one would be. So if the decimal terminates, or if it repeats, or if it's a fraction, then all of those are rational numbers. They are exact numbers where we know the entire number. But now if we're looking at irrational numbers, those ones are approximate numbers. Now those cannot be written as a fraction. We can't write any irrational number as a fraction. And if we were to put this in our calculator, the decimal would go on forever and the numbers would all be random. So those would definitely be approximate because we don't know what the end of the number is. The number is entirely random. We'd end up rounding somewhere and we would cut off all these digits and we wouldn't know what the exact number is. And that's why these ones are considered approximate numbers or irrational numbers. So if we're looking at this chart here, you might have seen this before. We have a bunch of different number groups. So we have natural numbers. Those are the ones in here. Now, natural numbers and whole numbers are really, really similar, except one of them has a 0 in it and the other one does not include the 0. Now, how I remember is that whole numbers, this O here, that looks like a 0. And that's how I remember that those are the ones that include the 0 and so on. So natural numbers are just numbers 1, 2, 3, 4, 5, 6, 7. It does not include negative numbers. And whole numbers are the same thing, 1, 2, 3, 4, 5, 6, 7, 8, and so on, except it also includes the number 0. Now, if we're looking at integers, those also include 0, 1, 2, 3, 4, 5, 6, 7, but it now includes negative numbers. So we could keep going here, -5, -6, and so on. This could go up to 11, 12, and so on. Now, rational numbers, those are the ones we just talked about. Those are the ones that we can write as a fraction, or they have repeating decimals. That's what we see here. or they have a decimal that terminates. So those are all rational numbers. Also, regular numbers are also rational numbers. So by regular numbers, I mean integers, natural numbers, and whole numbers. Just like regular number like a 3, that's also a rational number. And then finally, we have irrational numbers. Now, those are the ones that go randomly off your calculator forever, and we don't know what the end of the number is. So if we were to put pi in our calculator, that number 3.141599265, that's all I know of pi, but it's a bunch of random numbers and we never know the exact number. Remember, irrational ones are approximate numbers, whereas rational numbers are exact. So finally, let's fill out this chart in example 4. Let's use our calculator to find the value of each of the following radicals. Determine if this radical is exact, aka repeating or terminating decimal, or if it's approximate, aka if it continues on forever and they have random decimal numbers. So in order to do this, all you're going to do is you're going to use your calculator. And of course, I wouldn't give you a question exactly like this on a test where you have to use your calculator because there's no calculators allowed. But you're going to plug all of these into your calculator, determine the value, and then determine if it's exact or approximate. So I'm going to fill out this chart and then I'll cut back. All right, so I put the values for if I plug them all into my calculator, and now let's see if these are exact or approximate. So for this one here, the decimal terminates, so that means it's exact. For the next one, the decimal goes on forever and it's random, so that's definitely an approximate one. The next one's definitely exact because that number, we know the whole number. And for the next 3 of them, all of these are approximate. So I'm just going to put approx for all of them because those decimals go on forever and they are random numbers. But for the next one here, this is definitely an exact number. We know the entire thing. Then for the next one, we have an approximate number because that decimal is random. Then for the next one here, look, this number can be written as a fraction, or if you put that in your calculator, you'll get a repeating decimal. So that means it is an exact number. And the last one would be approximate. So in this last little note here, we talked about this earlier. It says, when can you take the root of a negative number? So what I said there was that we could take the root of a negative number when the index, remember the index is the small number. So when the index, and by the small number I mean that one there, is an odd number. That's the only time we can take the root of a negative number. So for example, if we have the third root of negative 27, that is equal to negative 3, and that is because negative 3 times negative 3 times negative 3 is equal to negative 27. Another example we can look at here would be the fifth root, so 5 is an odd number, of negative 32. So that would be equal to negative 2, and that's because negative 2 times negative 2 times negative 2 times negative 2 times negative 2, so 5 times, is equal to negative 32. So these two numbers are odd.